So now we're going to begin section 4.2, which is real zeros of a polynomial function. And let's just keep in mind that a zero is a solution or it's an x-intercept on the graph. So the first theorem is the remainder theorem, and it just says that if you have a function f, okay, if f is a function, if you want to divide it by x minus c, the remainder is going to be f of c. Okay, so simply put, because that was a little wordy, if this is my function that I am dividing, so if I'm using this function here, which says f of x equals x cubed minus 4x squared minus 5, if I want to know what is the remainder, if I divide that by x minus 3, what I simply need to do is take my factor, solve it for x, and then whatever I get here, that is the root that I need to test. So I'm going to find f of 3 by substituting in a 3 in that function. So we're going to go ahead and substitute that in your calculator to see what you get. So we have 3 cubed minus 4 times 3 squared and minus 5. So my remainder, because f of 3 is negative 14, that means that that would be my remainder. And remember, a remainder is simply what you have when you divide a number by something that is not a factor. So for example, if I were to take 5 and divide it into 23, well, 5 is not a factor of 23. Okay, so I would have a remainder of 3. So just a reminder of what is a remainder. So if I divide x minus 3 into x cubed minus 4x squared minus 5, x minus 3 is not a factor, so x equals 3 is not a root, and my remainder would be negative 14. So let's do the same thing with part B. So again, you want to take your factor, set that equal to 0, and that gives you x equals negative 2. So we're going to test negative 2. So when we find f of negative 2, using that same function rule, substitute negative 2 into every place that you see an x. And I think it's a little easier for me to do this without the calculator sometimes. So negative 8 minus 16 minus 5 would be negative 29. Let me make sure though. 8, 16, and 5. Yep, negative 29. So that is your remainder. So it says find the remainder. And we did that by evaluating f of 3 and f of negative 2. So let's go ahead and do that. That's example 1. Now let's look at example 2. So in example 2, we're still trying to find the remainder, and we're going to use that same property. Okay, so I am going to take that positive 3, x plus 3, set it equal to 0, and find f of negative 3. and do the same thing. Find f of negative 1, and just be careful to make sure if you're doing this in your calculator that you do use parentheses around that negative. Alright, so go ahead and pause the video at this time to find your two remainders for f of negative 3, and then we're going to do the same thing. We're going to find f of negative 1. Okay, so when we evaluated f of negative 3, we determined that the remainder is 130. So the answer to part A is 130. However, when you evaluate part B, we actually get 0. So what does that mean whenever your remainder is 0? Well, again, if you're dividing a number by another number and the remainder is 0, that means that that is a factor. So x plus 1 is a factor. It is a factor, and we know that because our remainder is 0. Okay, so x equals negative 3 is not a root, but x equals negative 1 is a root of this function. So if I were to graph this, I would expect to see an x-intercept at negative 1, but not at negative 3. So what that says is that in that last example is let f be a polynomial function. Then if x minus c is a factor of f of x, or that function, if and only if f of c is 0. So going back to that last example, when we test the actual root that would be related to that factor, if we get 0 at that specific root, then that factor is indeed a factor of the polynomial, and that point is an x-intercept.